is a rod that's captured between two rigid walls. It's then heated on its left half and cooled on the right half. Our question is to find what is the stress in the rod. We also en route will find the displacement field, and I would anticipate that that center node would move to the right. I'm actually going to model this with two separate rod elements, each 100 millimeters long. The area is 1,000 millimeters, so this is the same sized rod as we used in an earlier example, but I've chosen different material properties. I have a Young's modulus, I have coefficient of linear expansion, and here I put in this heat conduction coefficient. Why is that there? Well, that's just a little bit of a red herring to make people sure that they know what they're doing. And I find on exams that it sometimes really strikes terror in people's heart to have extraneous information. But heat conduction won't have anything to do with this problem if we've been given the temperature field a priori. The solution will be done with two rod elements, and we'll start out with the general equation for a single element. We've seen this before. One of our main goals now will be to calculate the equivalent nodal load shown on the right. And in our problem, using our material constants, we're going to get, here is the equivalent nodal load that will tend to expand the element that's been heated, and it turns out to be 100,000 newtons. The force on the right element is going to turn out to be 150,000 newtons, tending to compress the element. Equivalent nodal loads do assemble in the same way that external forces do. In fact, they play the role of an external force in this problem. When we set up our two separate equations for the two elements, we have these disjoint equations, and we already have studied how to handle the mechanical loads here, and so we'll just handle the equivalent nodal loads the same way. And when they're assembled, you see that there is some additive effect at the center node here, so you end up with 250,000 newtons to the right at the center node, 100,000 to the left at the left node, and here actually 150,000 to the left at the right node. I'll sketch those when we get to that figure in the next slide. Well, in this case, because our mixed boundary value problem has constrained the displacements at the two ends, and we don't know the reactions there, but we have no live loads at the center node, we then can uncouple that second equation and solve for the displacement, and we get 0.125 millimeters, which is to the right, and that confirms our initial guess that the center node should move to the right. I'll sketch the loads on this next figure. The displacement is already shown to the right, and then the thermal loads, you see, we're acting to the left at the left end, and then quite an enormous load here at the center to the right, and then the thermal load to the left there. And you can see that that's going to put the left member in tension and the right member in compression. Now, at this point, we've solved the typical discrete problem for displacements, and that's the basic problem. But now we'd like to recover the element properties of stress and strain. So we know that equilibrium says that our rod should be at the same stress. Let's check that out. We go into our stress-strain law, and we can calculate the mechanical strain directly from the displacement field, which was 0.125 millimeter over 100 millimeter length. So that's our strain in the left element. Then the thermal strain came about because of the temperature and the expansion coefficient, and has this value. So when you calculate the stress in the left rod, you come up with this value of 25 megapascals. I've also done that calculation for the right rod, and it comes out the same. So you'll just have to take my word on that. And that would be a good side calculation for you to do, because the numbers would be different, you see. Our second problem has to do with a combination of a rod and a beam, and we're going to have both mechanical and thermal loading. The beam extends from wall to wall between two rigid walls, and then there's a rod that's connected to it by pins both at the top and at the bottom. The beam is not segmented. It carries through this pinned region as a continuous beam. We're going to put a live load of 400 newtons downward at the center of the beam rod situation, and then we're going to cool the rod 200 degrees Celsius. And the question is, what way does the center of this beam move? Does it go up or down? And we wouldn't have much feeling for that, I think, on the first try. You can look at the stiffnesses of the rod, you can look at the bending stiffness of the beam and try to make a guess, but I think on the first problem you'd have no hope. Our solution has 7 degrees of freedom that are important. Luckily, the ones out around the periphery of the problem are going to be constrained, so they will drop out. Here's a sketch of the degrees of freedom, the 2 rod degrees of freedom at the top, and then there's 6 beam degrees of freedom at the bottom. We're emphasizing just the planar aspects of the problem. We're not worried about out-of-plane bending. And I'm not worried about the axial compression of the beam. There are no loads tending to bring in the axial stiffness, so we won't model that degree of freedom for the beam. We're going to break the beam into the 2 elements and the rod into one, so we have a 3-element, 7 degree of freedom problem. Now, if I constrain those degrees of freedom at the left wall, at the right wall, and at the top wall, we really only have 2 remaining degrees of freedom, 3 and 4. But by symmetry, degree of freedom 4 is going to vanish. So we really can just concentrate on what happens to that vertical degree of freedom 3 when the system has been assembled. I'll show the assembled matrix in the 7 by 7 form, and I'll just use dots where I don't care what the entries are. We do know that there's a live load of 400 newtons acting downward on degree of freedom 3. We know that we're going to pick up an equivalent nodal load due to the temperature load in the rod that we have to calculate yet. At degree of freedom 3, we're going to get stiffnesses that are due to the lateral bending of both beam elements, and that leads to this 24 EI term. And then we're going to get the axial stiffness of the rod element, and those are additive. All 3 of those effects are additive from the 3 joining elements. And then here's our displacement U3 on the right. So we need to find the equivalent nodal load for the rod. It follows that conventional rule that we showed. The temperature in this case is negative because it's cooled, and we end up with this pair of 200 Newton forces shown on the right. The important one is the vertical 200 Newton force at node 3, which is positive. We'll add that 200 newtons upward in with the 400 newtons downward, which was the mechanical load, to get the final equation of equilibrium, and write it out in scalar form. We have the sum of the stiffnesses, the displacement. Solve for the displacement, and we get 0.45 millimeters downward. And that's to be expected now, because with the mechanical equivalent of the thermal load, we now have a way to say, oh yes, the beam should deflect downward because the thermal load wasn't as big as the mechanical load. Problem 3 is a 2-dimensional problem with a constant strain triangle. This is a plane stress triangle as shown, It has a pin at the left and a roller at the right. And of course, using a single element for this example is a little bit presumptuous, because this constant strain triangle will maintain straight sides when it's heated, cooled, pulled, pushed. And that's more appropriate when it's embedded as one of many elements in a total assembly. But for us, it's okay, and we'll just treat it as a kind of a degenerate assembly. The element's going to be heated 100 degrees Celsius, and the question is, what is the vertical load at the top node? So we're interested in finding what the force is going through here that reflects the 100-degree heating and would cause similar strain. Now the element's symmetric about the base, and so we wouldn't expect a horizontal force at that node. The model itself is made of aluminum 10 millimeters thick, so it's really a plate. It's pretty husky, and we're going to expect pretty high thermal loads here to stretch it. The materials are just the common aluminum material properties. The shape function matrix for the triangle is also given as a part of the problem statement. It's here, and I have figured out the components by looking at the equations for the inclined lines and so on. Now in our solution, we use the standard formula for equivalent nodal loads due to a thermal load, and originally it's a volumetric integral. In our case, we're going to put it into a summation form because we think we can get by with fewer calculations than one normally would. In particular, we only want the component F6. In other words, the vertical load on that vertex at the top. This means that in the summation form, if were this Fi and the B were B, would have been Bji, then the 6 occurs in this location. That's a little tricky, and I find that the transposition is a lot more tricky operation than people think. The reason is we're trying to locate terms back in the original form of the matrix, not in the transposed form. And so if the matrix B is characterized by rows I and columns J, and then if we transpose it, we reverse those roles. But I'm interested in the original form, and so when we come up with the Bj6, it means we're looking at the 6th column in the original matrix form. Then we have the generalized Hooke's law and the strain matrix. Now, because we only need the 6th component of the force, we then see that we only need to look at the 6th component or the 6th column of the B matrix. And that will let us simplify the calculation of the B matrix, which I show here. B is D times N. Now, if I use a summation form, what I'm saying basically is that we have Bi6 equals Di, and let's use a summation J times Nj6. This free index goes with this one, and then there's a sum over J in between. Now what I've written out here then shows the 6th column of the shape function matrix. That's all I'm going to need, and when I do the relevant calculations to get the 6th column of the B matrix, then that's all I need to do. Now the material law is a common plane stress law. The pre-strain term is pretty easy because it's just the strain due to the temperature load. We worked that out before in plane stress, and you only get the strains in the X and Y directions here, which are, for us, principal directions of an isotropic material. So it turns out that all the terms in the integral are constants, and the integral itself reduces to an area integral, which is no problem. Then the constants, when written out, have all of these terms in general, but because of zeros in the B matrix, we knock out some pretty big terms here. And then because of a zero in the G matrix, which is the generalized Hooke's law, we knock this out. And we really come down to only two terms contributing. I'll write that last equation out using the symbols involved. So we bring in our temperature effect and our material properties. I'm showing the area here. Now the area is simply AB because A is the half base, and so I can make that replacement, which then allows the cancellation of the B's. The material terms I can gather together, and I get a cancellation of some of the Poisson ratio terms. Then by putting in the proper material and geometric constants, I come up with this equivalent nodal load due to that temperature in the triangle at the tip here in the vertical direction. And it's a positive load trying to stretch the triangle. So what we've done is taken a heated triangle on the left here and replaced it with a triangle that has the mechanical loads shown on the right. We didn't calculate the reaction forces at the base, but you can get a sense of the magnitude, that it takes rather strong mechanical loads to strain a plate that's a pretty husky plate as much as this temperature change of 100 degrees would require.